Welcome back to Bite-Sized Breakthroughs, where we unpack the latest advancements in the world of AI. Today we're diving deep into a fascinating research paper exploring the in-context learning capabilities of transformers. Joining me is Dr. Paige Turner, a leading researcher in this field, and Professor Wide Spectrum, a renowned expert in AI and machine learning. Dr. Turner, thank you for joining us. Could you start by introducing the paper and its main focus?
Thank you for having me, Alex. The paper, titled What Can Transformers Learn in Context? A case study of simple function classes, delves into the intriguing question of whether and how transformer models can learn new tasks or functions at inference time without the need for any parameter updates. This contrasts with traditional machine learning approaches where models are trained beforehand and then applied to new data.
That's a very interesting concept, Dr. Turner. Could you provide some historical context? What were the key observations or breakthroughs that motivated this research?
Sure. The paper is inspired by the emergence of in-context learning in large language models like GPT-3. These models demonstrated the ability to learn new tasks from prompts containing examples without requiring any fine-tuning. For instance, you could provide a few English-French translations as a prompt, and the model could then correctly translate new French words into English. However, it wasn't clear whether these models were truly learning new tasks or simply relying on patterns and examples they encountered during their extensive training.
Professor Spectrum, you've been working in this field for a long time. What are your thoughts on this initial observation of in-context learning in large language models?
Well, Alex, it was certainly a surprising and exciting discovery. It hinted at a potential for far greater flexibility and adaptability in AI systems. But as Dr. Turner mentioned, there was a lot of skepticism about whether these models were genuinely learning new things or simply memorizing and regurgitating information they'd seen in their vast training datasets. This research delves into that question, and that's what makes it so valuable.
So, Dr. Turner, how did the researchers approach this question? What were the key contributions and innovations of their work?
The paper's central innovation is to formalize the notion of in-context learning as a well-defined problem of learning function classes at inference time. This allows for a more controlled and rigorous investigation compared to studying the behavior of pre-trained large language models. The authors then designed experiments to train transformer models from scratch to in-context learn several simple yet important function classes.
Could you elaborate on what you mean by function classes? What types of functions were they working with?
Sure. They started with linear functions, which are fundamental in many areas of machine learning and represent a simple yet important starting point. They also expanded their investigation to more complex functions like sparse linear functions, decision trees, and two-layer ReLU neural networks. These functions represent different levels of complexity and often require specialized algorithms to learn them effectively.
Professor Spectrum, can you give us a quick overview of those function classes for our listeners? We might not be familiar with all of these terms.
Certainly, Alex. Linear functions are simply lines or planes, represented by an equation like y equals mx plus c. Sparse linear functions are similar, but have a limited number of non-zero coefficients, which makes them particularly useful for tasks involving sparse data. Decision trees are hierarchical structures that divide data into progressively smaller groups based on a series of decisions about its features. Two-layer ReLU neural networks are simple neural networks that use a rectified linear unit (ELU) activation function to introduce nonlinearity, making them more powerful than linear models.
Thank you, Professor. So, Dr. Turner, what was the general methodology used in this research?
The researchers trained decoder-only transformer models, which are similar to the architecture used in GPT-3, from scratch. They provided these models with prompts consisting of in-context examples, which were input-output pairs generated from a specific function class. For instance, if they wanted to train the model to learn linear functions, they would provide a sequence of inputs and their corresponding outputs, calculated using a randomly chosen linear function. The model then learns to predict the output for a new query input based solely on these in-context examples.
That's quite an interesting approach. How did they measure the model's success? What metrics did they use?
They primarily used normalized squared error. This metric measures the difference between the model's prediction for a query input and the true function value, normalized by the input dimension. This gives them a standardized measure of the model's accuracy. They also compared the performance of their trained transformers to other relevant algorithms for each function class, such as least squares, lasso, greedy tree learning, and gradient descent for training neural networks.
Professor Spectrum, how does this methodology compare to existing methods for in-context learning? What are the potential advantages or limitations?
It's a significant advancement in our understanding of in-context learning, Alex. Previous research often relied on the behavior of pre-trained large language models, which are complex and less controlled. This paper's approach of training models from scratch on specific function classes offers a more controlled and systematic way to investigate this phenomenon. The study also differentiates itself by explicitly investigating the robustness of in-context learning to distribution shifts between training and inference.
Dr. Turner, could you elaborate on this concept of distribution shifts? It sounds crucial.
Of course, a distribution shift happens when the characteristics of the data used during training differ from the characteristics of the data the model encounters at inference time. This is a common problem in real-world applications of machine learning. In this study, the researchers explored several types of distribution shifts. For example, they tested the model on prompts where the input distribution was skewed, the output values were noisy, or the in-context examples, and the query input came from different subsets of the data.
That's fascinating. So did the transformers perform well even under these distribution shifts?
The results were very encouraging, Alex. The model's ability to in-context learn linear functions was quite robust, even when the input distribution was skewed or the output values were noisy. Interestingly, they also found that the model's performance generally improved as they increased the model's capacity, meaning the number of parameters in the model. This highlights the importance of model capacity for achieving accurate and robust in-context learning, especially for more complex tasks.
This is getting exciting, Dr. Turner. Could you provide some concrete examples of the results they found? What specific function classes did the transformers excel at? And what were the key performance measures?
Certainly. Let's start with linear functions. They trained a transformer model with 9.5 million parameters to in-context learn linear functions in 20 dimensions. They found that the model's error was comparable to the optimal least squares estimator, a benchmark algorithm for linear regression. This means the transformer was essentially performing linear regression in a single forward pass without any explicit optimization steps. Moreover, when they provided the model with 40 in-context examples, it achieved an error of only 0.006, indicating highly accurate learning.
Wow, that's impressive. What about the more complex function classes?
They also achieved remarkable results with sparse linear functions, decision trees, and two-layer neural networks. For sparse linear functions, where the weight vectors have a limited number of non-zero coefficients, the transformer achieved performance comparable to lasso, a specialized algorithm for learning sparse models. For decision trees, the transformer significantly outperformed greedy tree learning and boosting algorithms, especially when the number of in-context examples was limited. For two-layer neural networks, the transformer achieved comparable performance to a neural network trained using gradient descent on the in-context examples. This highlights the fact that transformers can effectively encode complex learning algorithms that mimic the behavior of traditional algorithms without the need for iterative optimization steps.
Professor Spectrum, how significant are these findings? What are the broader implications for the field of machine learning?
This research is groundbreaking, Alex. It demonstrates that transformers, a type of neural network architecture, have a powerful and previously underestimated capacity for in-context learning. It challenges our understanding of how these models function, suggesting they may be capable of far more than simply memorizing patterns. This has tremendous implications for various aspects of machine learning, particularly in areas like few-shot learning and algorithm discovery.
Could you explain those two areas in more detail, Professor?
Certainly. Few-shot learning is a challenge in machine learning where we want to train models with very limited amounts of data. The ability to learn from a few in context examples makes transformers very promising for these scenarios. Algorithm discovery is another fascinating area. If we can understand the algorithms that transformers implicitly encode during in context learning, we might be able to reverse engineer them and discover novel and efficient algorithms for solving various problems.
That's a truly exciting possibility, Professor. Dr. Turner, what are your thoughts on the limitations of this research and the future directions it points to?
While these findings are impressive, it's important to recognize their limitations. The study focused on relatively simple function classes, and further research is needed to investigate the limits of in context learning for more complex and realistic tasks. The training data used in the study was synthetic, so we need to explore how these findings translate to real world data, which is often more complex and noisy. Additionally, the study primarily focused on transformers trained from scratch, and it's essential to examine whether these findings hold for pre-trained large language models, which often exhibit remarkable in-context learning capabilities.
Those are valid points, Dr. Turner. What are some of the key future directions you see emerging from this research?
I think the most crucial direction is to investigate the relationship between the complexity of the function class, the capacity of the model, and the number of prompts required for successful in context learning. This could help us understand the limits of this capability. We also need to explore the potential of curriculum learning for training large language models. This technique, which involves gradually increasing the complexity of the training data, could significantly reduce training time and resource requirements. Additionally, we need to compare the inductive biases of different model families in the context of in-context learning. This could reveal which architectures are best suited for different types of tasks. Finally, we should work on developing techniques to reverse engineer transformer models to extract and formalize the learning algorithms they implicitly encode. This could lead to the discovery of novel algorithms for various learning problems.
Professor Spectrum, how do you think this research will impact the field of AI in the coming years?
I believe this research has the potential for a significant impact on AI, Alex. The ability to learn new tasks from just a few examples could revolutionize how we develop and deploy AI systems. This could lead to more flexible, adaptable, and efficient AI systems that can handle a wider range of tasks with less data and computational resources. It could also lead to breakthroughs in areas like algorithm discovery and the development of new, powerful AI tools.
So, Dr. Turner, to wrap things up, what are the key takeaways from this groundbreaking research?
This research has shown that transformers possess an extraordinary ability for in context learning, allowing them to effectively learn various function classes, including linear functions, sparse linear functions, decision trees, and two-layer neural networks. This capability demonstrates robustness to distribution shifts, suggesting that transformers are not just memorizing patterns, but are capable of generalizing to new data. The study also reveals the importance of model capacity and explores the benefits of curriculum learning for accelerating training. This research paves the way for future investigations into the limits of in context learning, the potential for algorithm discovery, and the broader implications of this powerful learning capability for the field of AI.
Thank you both for joining us today and sharing these fascinating insights. We've gained a deep understanding of this groundbreaking research, its implications, and the exciting future directions it opens up. Be sure to stay tuned for more bite-sized breakthroughs as we continue exploring the latest advancements in the world of AI.